Hello, students. Welcome to the Remedial lecture series that we have started in this week. And today, in this lecture series of Remedial classes, we are going to discuss properties of Laplace transform. Again, some very important points that will be recovered in this case of Remedial class that we are going to discuss today. That is properties of Laplace transform. In our last class in this Remedial lecture series, I have started discussion and introduction on Laplace transform, and a very important point has came out from that discussion that Laplace transforms can be used to solve linear constant coefficient differential equation. We can get a total solution of linear constant coefficient differential equation by the help of Laplace transform also. In our previous unit number 1, when we have discussed linear time invariant systems, we have covered linear constant coefficient differential equations and the differential equations also. And in that case, we have also solve the linear constant coefficient difference equations by the help of particular solution and the homogeneous solution. Now in the case of Laplace transform, we take the help of Laplace transform to solve the linear constant coefficient differential equation to get the total solution of the differential equations. Now today we are going to start have a discussion on the properties of Laplace transform. What are the properties of Laplace transform? The properties are very simple. We have already told you, I already told you in my previous lecture that it is a counterpart of Z transform. The relationship of Z transform with DTFT is similar to have a similar impact on the relationship of Laplace transform with CTFT. As the properties of CTFT, we have already covered the properties of CTFT. The same type of properties also exist for in the case of Laplace transform. We have already seen that Laplace transform can be reduced to CTFT in a case when the S plane S is equals to sigma plus j omega. When sigma is equals to 0, then the Laplace transform can be reduced to CTFT. Now let us start the properties of Laplace transform. First property is linearity. We have two signals here, x1t and x2t. The Laplace transform of x1t, if it is defined as x1s, whose ROC is r1, the Laplace transform of signal x2t is defined as x2s, whose ROC is r2. Then what will be the Laplace transform of a linear combination of these two signals, that is a1x1t plus a2x2t? The resultant Laplace transform will be a1x1s plus a2x2s, and the resultant ROC will be the common area, that is the common area of ROCs of R1 and R2. That is, it is the common area of between R1 and R2. Next is time shifting property. If Laplace transform of xt is defined as x of s, whose ROC is R, then the Laplace transform of xt minus t0 will be defined as e raised to minus of s t0, e raised to minus of s t0 xs. The ROC will remain same, that is R. Very important property in case of time shifting. If xt is shifted by x of t minus t0, the Laplace transform will be e raised to minus of s t0 xs. Similarly, this is a time delay. Similarly, if the shifting is in time advance, then if it is xt plus t0, then the Laplace transform will be e raised to plus s t0 x of s. ROC will remain same. And next is shifting in S domain. If xt has a Laplace transform of xs with ROC equals to R, then e raised to s naught t xt. If we have a signal e raised to s naught t xt, then its Laplace transform will be x of s minus s0, x of s minus s0. That is shifted. The signal is shifted in frequency domain, and its ROC will be the ROC previous ROC plus the real part of s0. Time scaling. If xt has a Laplace transform of xs whose ROC is R, then xat will have a Laplace transform equals to 1 upon modulus of a xs by a. 1 upon a xs by a. Here I have taken an example. If what will be the Laplace transform of x minus t? Is basically in this case a is equals to minus 1. So x of minus t will have a Laplace transform x of minus s, and its ROC will remain same. ROC in this case will be R by A, and in this case ROC will be R by 1, and in this case the ROC same shall remain same. It will be equals to R by modulus of A actually. Convolution property, very popular property. We have already covered this property in CTFT. We have covered this property in DTFT. We have already covered this property even in Z transform. The basic essence of the property is same, that is convolution in time domain, it results into multiplication into frequency domain. Here we have two signals x1t and x2t whose Laplace transforms are x1s and x2s. Their ROCs are r1 and r2. That is, if these two signals are convolved, that is, we have a signal x3t which is the convolution between x1t and x2t, then their Laplace transform will be defined as x3s, and it is nothing, it is the multiplication between x1s and x2s. Very important thing is that the ROC is the common area between R1 and R2. The ROC is the common area between the ROCs of R1 and the ROC R2. Conjugation property. If xt has a Laplace transform equals to x of s whose ROCs are, then x conjugate t will have a Laplace transform equals to x conjugate s conjugate. ROC will remain same. And now comes seventh number property, that is very important property, differentiation in time domain. We'll see these properties when you are going to solve the differential equations. Here it is defined like this. If writing is very unpredicted, sorry for the interruption. Now we'll see the property differentiation in time domain. If ft has a Laplace transform defined as f of s whose ROCs are, then the Laplace transform of f dash t is basically dft by dt. The Laplace transform is defined as sfs minus f0, the initial value f0, sfs minus f0. Sorry for the writing here, but you can very clearly understand this. The Laplace transform of ft, if it is defined as fs whose ROCs are, then the Laplace transform of f dash t, that is dft by dt, will be sfs minus f0. Again, what will be the Laplace transform of f double dash t, that is d2ft by dt square. D2ft by dt square will have a Laplace transform equals to s square fs minus of s f0 minus of f dash 0. Similarly, what will be the Laplace transform of f raised to nt? If it is differentiated n times, then it will be s raised to n fs minus s raised to n minus 1 f0 minus s raised to n minus 2 f dash 0, like that, and like let it go to f raised to n minus 1 0. We'll see, we'll be having some questions either in first differential form or second differential form or maybe third differential form. We can very easily have this result. That is, for f dash t it is sfs minus f0. For f double dash t it is s square fs minus of s f0 minus of f dash 0. Next property is differentiation in s domain. If xt has a Laplace transform equals to xs whose ROCs are, then for minus t xt, the the Laplace transform will be dx of s by ds, and ROC will remain same. For xt, if Laplace transform is xs, then for minus t xt, the Laplace transform is dxs by ds. ROC shall remain same. Again, a very important property, property number 9. This in this page, in this sheet, we can see the properties are very important. These properties somehow come in our numericals, will be used in numericals. So please pay attention to these properties at most. We'll see integration in time domain. If xt has a Laplace transform equals to xs whose ROCs are, then for minus integral minus infinite to t x tau d tau minus infinite to t integral x tau d tau will have a Laplace transform equals to 1 upon s xs, and ROC is the common area between r and the real part of s greater than 0. Again, if xt has a Laplace transform equals to x of s whose ROCs are, then the Laplace transform of integral minus infinite to t x tau d tau will be 1 upon s xs. Uh, we are now again looking at the property we have already discussed in Z transform, that is initial value theorem and the final value theorem. What are these theorem in case of Laplace transform? If the function xt and its derivative x dash t are Laplace transformable, then the initial value theorem is defined as to calculate the initial value of the signal xt, its value will be x0, and accordingly in time domain its value will be limit t tends to 0 xt. And by using the Laplace transform, the value of initial value of xt, that is x of 0, will be calculated by the formula limit s tends to infinity as fs. So the initial value theorem says that to find out the initial value of a signal xt, that is x of 0, The initial value x of 0 can be calculated by the help of Laplace transform by the formula limit s tends to infinity sfs. Similarly, the final value theorem says that to calculate the final value of a signal xt, the final value is x infinite, and its value will be actually limit t tends to infinity xt in the time domain. By using the Laplace transform in frequency domain, the value is equals to limit s tends to 0 SFS. So please remember these two very important theorems, that is initial value theorem and the final value theorem. They may be asked as a theory question, and they may also be asked as a numerical part. Giving the value of Fs to you, the examiner can ask the initial value of a signal xt and the final value of a signal xt. The initial value is defined as limit s tends to infinity SFS, and the final value is defined as limit s tends to 0 SFS. Here, Laplace transform of some elementary functions are given for revision. You can remember these formulas. They can be used in some numericals. They can help you in some numericals. So, a quick review of the formulas is given here. The Laplace transform of delta t is 1. The ROC is the all values of s. The entire s plane is the ROC in this case. It is counterpart of delta n. Del n in that case of z transform, the z transform of the unit is delta function was 1 in that case also, and its ROC was the entire z plane. Similarly, ut has a Laplace transform equals to 1 upon s, and its ROC is real part of s greater than 0. Minus of u minus t is also having a Laplace transform equals to 1 upon s, but its ROC is real part of s should be less than 0. It is negative values or negative plane of s. Negative values of sigma here. E raised to minus of at ut has a Laplace transform equals to 1 upon s plus a, and the ROC is real part of s should be greater than minus a. Minus of e raised to minus at u minus t will again have a Laplace transform equals to 1 upon s plus a, and its ROC is real part of s less than minus of a. That means ROC in these two cases are sorry, algebraic expression of Laplace transform in these two cases or in these two cases are same, but they are identified only by the help of their ROCs. Similarly, cos omega naught t ut has a Laplace transform equals to s upon s square plus omega square. S is greater than equals to greater than 0. Sin omega naught t ut has a Laplace transform of omega naught divided by s square plus omega naught square, and the Laplace transform is ROC is real part of s again greater than 0. So here these formulas are given directly for your help when you are going to solve some numericals in your papers. Uh, have a look on these formulas, and in case you are not able to remember these, they are very easy to solve. To get the result in these cases, the result is very very simple. Here a very important formula of signal t raised to n ut is given. Please remember this formula. T raised to n ut has a Laplace transform. By solving it by the help of Laplace transform formula, the result is factorial n upon s raised to n plus 1. For t raised to n ut, the Laplace transform is factorial n upon n s raised to n plus 1. So that's all for today in this lecture, or remedial lecture of properties of Laplace transform. We'll discuss how to solve linear constant coefficient differential equation and get the total solution by the help of unilateral Laplace transform in my next lecture of the remedial lecture series. So kindly attend these lectures and get benefited. And if you have any query, you can contact me at my mail. Thank you. That's all.